Hello everyone. In this video, we are going to talk about the principle of conservation of angular momentum in the context of rotation about a fixed axis. While we have discussed about the angular momentum in case of rotation about a fixed axis in our previous video, we got one such expression which is d by dt of I omega is equal to tau. This was actually equation number 26 in our previous video. I hope you remember this. Otherwise, I will provide the link in the description box. If you want, you can watch that. So, this equation I am taking as 1 here. Where I is the moment of inertia, omega is the angular velocity and tau is the total external torque along the axis of rotation. And there we had one such equation too, that is vector Lz is equal to I omega into k cap. This was actually equation number 16 in our previous video, and I am taking this as equation number 2 here. I will provide the link for this in our description box, so please see that if you don't remember this equation. Okay, now you see from this equation vector Lz, that is the angular momentum along the z axis, equal to I omega into k cap. That I omega is the magnitude of this angular momentum and k cap, it is actually gives us the direction along the z axis. Okay, so from this equation number 2, the magnitude of the angular momentum along the z axis, that is simply Lz. We don't want to put a vector sign here because we are taking the magnitude. This can be written as what? I omega, and I am taking this as equation number 3. Alright. Now, if the external torque is equal to 0, if the external torque equal to 0, that means if tau equal to 0, then this expression becomes what? Equation number 1 becomes d by dt of I omega equal to 0. Okay, derivative of something equal to 0 means that something is a constant. So, d by dt of I omega equal to 0 implies I omega equal to a constant. Okay, see from this expression 3 we have Lz equal to I omega. So, we can write L subscript Z equal to I omega equal to a constant. That is when torque tau equal to 0. I am taking this as equation number, this as 4. Okay. So, that is when torque is equal to 0, the angular momentum along the z axis, which is equal to I omega, is conserved, or it is equal to a constant. Okay. Now, for symmetric bodies means bodies which are symmetric about the axis of rotation. We have total angular momentum of the body vector L as vector Lz. This was actually equation number 19 in our previous video. Okay, so for symmetric bodies, here we got L is equal to a constant, L is equal to I omega equal to a constant. So for symmetric bodies, this Lz, which is the magnitude of, this Lz, which is the magnitude of vector Lz, that can be replaced by what? L. Okay, L is actually what? The magnitude of vector L. Okay, vector L is actually the total angular momentum of the body. Okay, for symmetric bodies, this vector L, total angular momentum of the body is equal to vector Lz. Alright, so for symmetric bodies, this L is equal to what? Lz, and this is equal to what? I omega, and that is a constant when torque is equal to 0. Okay, I am taking this as 5. So, this equation 5, this is actually the expression for the law of conservation of angular momentum for fixed axis of rotation. We have already discussed about a general law of conservation of angular momentum of a system of particles in our previous video. I will provide the link in the description box. If you want, you can watch that. See, there we got one such expression, that is d vector L divided by dt is equal to vector tau external. That is, the time rate of the total angular momentum vector L of a system of particles about a point is equal to the sum of the total external torque or sum of the external torque or torques due to the external forces acting on the system taken about the same point. Okay, now if this vector tau external is equal to 0, then this d vector L divided by dt becomes equal to 0, no? Okay, d vector L divided by dt, that becomes 0. Okay, that means what? Vector L is equal to a constant. That is, derivative of something equal to 0 means that something equal to a constant. So, vector L equal to a constant. That is, if the total external torque on the system of particles is 0, then the total angular momentum of the system, that is vector L, is a constant. That is, it is conserved. This is the general law of conservation of angular momentum of a system of particles. And this equation 5 now, this is actually the required form of conservation of angular momentum for fixed axis of rotation. Okay, this is the required form of conservation of angular momentum for fixed axis of rotation. Okay. Now, see this law of conservation of angular momentum and this equation number 4, which is L is equal to I omega equal to a constant, can be applied to so many situations that we come across in our daily life. For example, you just sit on a swivel chair. Okay, it is actually a chair with a seat able to be turned on its base to face in any directions. You might have seen this, you might have sat on this. Okay, now fold your arms close to your body. Keep it close to your chest and make sure that your feet is not touching the ground. Then ask your friend to give a little spin on the chair so that you and the chair rotate. Okay, you and the chair rotate in a particular direction, either in clockwise direction or in anti-clockwise direction. Okay, and you will have some angular momentum. What? L is equal to I omega. Alright, now stretch your arms wide. Stretch your arms out wide. You get slowed down. Your angular speed gets reduced. Now, if you bring back your arms close to your body, you start to spin faster again. That is, your angular speed increases. So, what is actually happening here? We know that momentum is always conserved. We are neglecting the frictional force here. Here, angular momentum is actually equal to what? Moment of inertia and the angular velocity. Okay, or moment of inertia into angular speed. So, moving your arms in and out changes your moment of inertia. So, when you move your arms, arms in close to your body, your moment of inertia decreases. When you move your arms in close to your body, your moment of inertia decreases. So, moment of inertia decreases. Okay, moment of inertia decreases. So, to conserve the angular momentum, your angular speed increases. Okay, for example, you just imagine this angular momentum as 10. Alright, it is a product of moment of inertia into angular speed, no? So, let the moment of inertia be, for example, what? Not 10, okay, I'm just taking it as 100. So, 100 is equal to, I'm taking the moment of inertia as 50 and angular speed as 2. Okay, so when the moment of inertia decreases, you just imagine it has decreased to 25. Okay, but we want to conserve the angular momentum, that is we want to get 100 again. So what happens to the angular speed? It increases from 2 to 4. Then only 25 into 4 will give you 100. So when moment of inertia decreases, angular speed increases and you spin fast. Okay, next, when you stretch your arms out, your moment of inertia increases. So to conserve the angular momentum, your angular speed decreases. Okay, so you spin slowly. Alright, when the moment of inertia increases, so coming back here, or when it increases, coming back here, 25 to 50. Then to conserve this angular momentum to get 100 again, what happens to the angular speed? Angular speed decreases 4 to 2. Okay, angular speed decreases means you spin slowly. Okay. So in this video, we have discussed about the conservation of angular momentum in the context of actually rotation about a fixed axis, and we have discussed about one example. I hope you understood this. Thank you.